Hi everyone. In the last video we talked about how Einstein's theory of relativity requires us to consider space and time as being combined together in some kind of unity. In the same way that Maxwell's equations require us to consider the electric and magnetic fields combined together. The interesting thing is this: as we push through these notions at the foundation of mechanics through the rest of Newtonian mechanics, other things change as well, and we find that energy and momentum also will combine together in a fundamental unity. But before we get there, let's just talk about momentum for a second. We basically, in order to incorporate relativity into our notion of momentum, we just use the new formula for mass with gamma factor in there, and that's straightforward. The interesting thing here is that, remember, there's a velocity inside this gamma factor. So this is actually a complicated formula, has a complicated dependence on speed. But if we run through the same logic we used originally to derive the kinetic energy for a simple particle in motion, 1/2 mv squared, if we use that same logic, it's going to require some calculus now. This is the final result. We get this kind of formula where we've got gamma minus 1 multiplied by mc squared. M here represents the rest mass. It's not the actual mass of the moving particle, because that has got a gamma factor in front of it. It's the mass of that particle as if it weren't moving at all. Now, that's easy to understand because, you know, this gamma factor reduces to 1 when velocity is 0. So, you know, the gamma m is equal to m in that special case. So, you know, that's just a straightforward application of this momentum formula. And that's the kinetic energy for relativity. Now, if I were to rearrange this definition, go through a little bit of algebra, basically in order to eliminate this v, if I were to rearrange, basically there's a square root inside this gamma factor. If I were to rearrange this to eliminate that square root, you know, essentially squaring both sides, rearranging, I get a formula that looks like this. But here, instead of E, what I have is gamma mc squared, all of that squared. And so that is the same formula as my definition of momentum. But what Einstein recognized is that that combination here is actually a type of energy. You know, it's got the same units as energy. And basically, this motivates not only redefining momentum, but redefining energy as well. And here we've got gamma mc squared. And as a simple consequence of this redefined energy, when we're at rest, gamma goes to 1, there's still a net energy associated with a particle, even if it's not moving at all. That's called the rest energy. Rest energy equals mc squared. This is the famous formula, E equals mc squared. It's a consequence of all this. And so basically what that says is that even though a particle's not even moving at all, it still has a certain amount of energy just by virtue of its very existence. And that energy can be tapped into and transformed in various ways. And so that generalization of energy is useful. And this formula, this intermediate formula that I was using to make that argument, this actually shows how the energy and momentum are combined together in one unity. If momentum changes, energy has to change with it. And they kind of move, you know, they move together. So in this formula, we've got energy, momentum, and mass all combined together in one formula. Here we've got energy, speed, and mass. Here we've got momentum, speed, and mass. And so, you know, in various contexts and various problems, you'll want to use different formulas to get at different things, right? So if I'm given a problem in which I know the energy and I know the speed, and I want to know the momentum, let me change that. If I know the energy and the speed and I want to know the mass, I would use this equation, because I got energy speed and mass in this formula. If I've got mass and momentum, I need to calculate the kinetic energy, or the energy. I'd use this formula. If I were given a problem in which I had the original combination, if I've got speed, energy, and I want to know momentum, then I want to use this central formula, which is kind of an algebraic combination of all these. So 1, 2, 3, 4. These are the 4 fundamental formula that we'll need in order to solve any of these problems associated with energy and momentum in relativity.